I am Armand Hopkins, and today I'll be presenting my GoldSim radionuclide simulation senior capstone project. So, to start, the project overview. In this project, we were tasked to develop a radionuclide impact screening tool using the GoldSim software. We were instructed from a team member from the Savannah River site named Steven. The software is made to predict radionuclide migration through soil and help us estimate groundwater concentrations. Some of the things that were watched through this simulation was solubility, infiltration rate, depth of the water table, and the release amount. The tool output showed us the maximum contaminant levels, which helped us determine if the water met safety regulations. The project goals include making sure we created a simplified screening tool to support the waste management assessment, integrating the GoldSim model for an automatic pass or fail with groundwater impact screening. We were also tasked to design an interface for the radionuclide properties while making sure our report is clear while also comparing the data charts to see the results. In this slide, I added a screenshot from my GoldSim simulation where it shows the MLC limit, the peak concentration, radio screening ratio, and the compliance status. Next slide is the conceptual design of the screening tool. So to start with the screening tool, we use a three-step process. Started with the peak concentration, then the screen ratio, and then compliance status. While conducting this simulation, we had to identify the worst case scenario showing the highest concentration predicted over the entire simulation time history. Then we had to compare the peak concentration with the regulatory limit. And finally, we had to translate the numerical ratio. It also is important to add the screening tool was connected to the groundwater concentration. So in the pictures, I have the MCL screening tool, and then I also have data from the MCL, which shows some of the results. And here, the data definition was 5.0 PCI divided by the liters per liter. And it also has the display unit, which is the PCI over the liters. Next slide is the generic transport model provided by the SRMC. So, in the generic transport model, we used a process simulation that was made to track the contaminant movement and the fate. We made sure the source and inventory management had contaminant properties and showed the characteristics. The inventory stored data like initial, mass, and half-life. There was also the physical transport and fate, which purpose was to stimulate the physical and chemical processes on how the contaminants move through the environment and also attract and calculate things such as groundwater, flow, and dispersion. Lastly, the generic transport showed the primary output. I added pictures of the transport which connected to the inventory inputs and the groundwater concentration. I also added the contaminant property transport result mode, which showed the description. It had the levels of the subcontaminants, which was 0, the number of model elements, which was 2, the number of graphical components, which was 1, input 6, outputs 121. The number of saved time history was 2 because I had to save my module because it was a couple complications with the simulation. The simulation structure, and then the memory time was, and then from there on out. The next slide will be the developing and integrating the screening tool within the model. The process for developing the simulation could be described into 4 phases. With the assistance of Stephen from Savannah Riverside, we started out with the design, which included identifying the peak, calculating the ratio, and issuing whether or not it was a pass or fail. We did start out with the tool, which helped us with data expression and finding a selector. Then we moved on to the model and integrating the testing using the tool to generic mode. We helped the primary technical step, which was resolving the syntax function. Lastly, the verification. We had to run the model and check all the outputs of all the elements. Here we have the MCL screening tool, and I checked the box of show history and show global changes, just to make sure we could see all the results possible. Then I added the contaminant model results, which showed the duration was 1,000 years, which is what Steven said all stimulations should have, which is 1,000 years. That's how I knew I was on the right track. And it started June 11, 2025 and ended June 19th of 3025. They both started at 12 a.m. and ended at 12 a.m. It was aligned, and it was 1001 scheduled update times, and that was very good for results. It was just good to see the inputs show outputs. So the simulation results using your screening tool. So my screening tool showed that our simulation verdict was a failure. The peak concentration was unfortunately 2 billion times greater than standard levels. Here I have visual graphs which show just how crazy the peak concentrations went. So starting on the bottom left, we have the basic final value results, and they start off, of course, at the bottom and just go crazy. They just have many spikes. They continue to keep peaking, and they go off the charts. Then we have this final value result, and they're all the way from 0 on up, and the results overlap, just showing just how great the standard levels were. And then I have another chart where I added color to it just to show how dynamic my results were. And I just think that's just a very good visual representation of how bad my simulation failed and how the peak went 2 billion times over the standard levels. Lessons learned and or future recommendations. So the lessons learned in this simulation would be the time data, which involves a linking of the functions in the primary model outputs, and that's very necessary to process the full time history data and avoid syntax errors. It's related to the units. Also, the value of isolation should be handled better going forward to make sure the primary transport model remains clear and not disturbed while running the simulations. Some things I would change in the future is the MCL, making sure the actions integrate with the scenario manager, which would help test the compliance of multiple different regulatory limits or concentration standards without having to edit the model input as much as I had to. Going forward, I would also enhance and develop the text graphic elements to help us understand the verdict of our simulation better, making sure we know whether or not it is a pass or fail without having to click as many different modules and right click in so many different elements, just making sure our results are more clear and concise and straight to the point. Lastly, my reflection. All in all, I would say this was a very hard project for me. It was very challenging dealing with the time analysis, modeling, integrations, and the element syntax for helping regulatory translations. All of these concepts were very new to me, considering that I'm a bio major. I have not had to do a lot of work that involved computer science concepts, so I'm actually very proud of myself. And with the help of Steven from the Savannah Riverside, I was able to conduct my simulation with the GoldSim software, which is also new to me. Even though my simulation failed, it was a success to me because I successfully input my data and created the different inputs in order to make a full simulation. That is the end of my project, and I would like to say thank you for everyone who was a part of this project and making sure this project helped us develop our skills and put us on our toes. Thank you.